Well, the application of the rocket engine what we have created in the previous video was to perform a numerical simulation with the different internal temperatures of the gases. So we have created the geometry of the rocket engine as per the dimensions which are given in the image, and we have used the ANSYS software and we have imported the geometry into the geometry module. And after creating the geometry, after importing the geometry, we have to mesh the geometry as seen in the mesh window. I will just open it. So this was the geometry which was created in Creo Parametric. Now we have imported it in the ANSYS software in the meshing module. So the objective is to analyze the flow variations inside the rocket engine. We have the inlet over here, and from here the gases will be entering into the combustion into the chamber, and it will be entered into the throat and followed by the nozzle, and this is the outlet of the total domain, which is the rocket engine. So we have created a mesh, and after creating the mesh, the necessity of the mesh is to divide the total domain or the total rocket engine into small chunk of elements, and we will be solving, the software will be solving the governing equations in the domain and will give us the results with respect to the variation in flow velocity, pressure, temperature, etc. It depends on the finding what we are performing. So let us go to the results and see what are the results. How do the results look like? And after meshing, we have to go to the setup and enter all the boundary conditions, which is nothing but the temperature, the pressure of the chamber. As I mentioned to you, the temperature and pressure will be very high in the rocket engine. And for this rocket engine, the pressure was something around, I believe it was something around 3.5 megapascals. And the temperature was something around 3000 kelvins, I believe. I'm not pretty sure, but it was in that particular range. So let us look at the results. How can we visualize the variations inside the rocket engine? So I will be showing you one more example. This is with respect to the 3D geometry what we have created in Creo and performed the simulation in ANSYS. And this is the CFD post module of ANSYS. Here you can visualize the results. How do they look like? So you can see that I have the inlet, the outlet, and the total wall of my rocket. So I'll just hide the wall right now, and we can create the contours. This is the pressure contour, temperature on the wall. Let me hide this. I'll go to volume rendering, and you can see this is I'll go to velocity or the Mach number. So this is how Mach number look like, the flow velocity looks like. You can see it is a very low velocity. Blue color indicates a low velocity range. This is a Mach number, and one Mach number is equal to 340 meters per second approximately. So you can see the Mach number is increasing to 4.5 at the exit. So let me just hide the outlet. You can see it is red color. So this is the highest Mach number, that is equal to 4.5 Mach number. So this is the flow visualization inside the rocket engine. How does it look like? We can also try to see the streamlines. I'll just hide the volume rendering, and we can see the paths of the line. It is called as streamlines. So we can animate, we can create an animation over here, and I believe it is under animation. So you can see the balls. These are just the symbols which are representing the flow, and it is a velocity streamline. You can see they are entering into the throat and they are exiting at high speed. So these are the visualization effects what we can see and understand the flow variation. So this was a small investigation with respect to the flow variation by changing the pressure, temperatures, and other factors. So this is a three-dimensional analysis what we are seeing, and this analysis was performed only inside the domain or inside the rocket engine. We have also performed additionally an analysis of a rocket engine but we wanted to see the variation of the flow at the exit or into the atmosphere. So for that purpose, we have created a two-dimensional case, because I'll just show you the figure because I don't have the files in this laptop. So this was the geometry. You can see over here, this is a two-dimensional sketch. And if I'm zooming in, this is the rocket nozzle, and we have the combustion gases entering from here and they are exiting at a very high pressure. And this was, the combustion temperature and pressure was around 9 megapascals and 3000 or 4000 Kelvin. So the amount of pressure and temperature and the design of nozzle exhausted the gases in this fashion. So this is the what do you call it, is a rocket. This is called a rocket plume, basically, like the visualization of the gases which are exhausting from the rocket. Let us just try to see in Google. You can see some images over here. For example, this image. So this is the plume which is coming out from the rocket. And in this particular research, we wanted to visualize the effects of, we wanted to see the way the plume is created. These are nothing but the shock waves. If I'm trying to zoom in, these are the shock waves. And this particular file was in other laptops, so I couldn't just open the file and show you. This is the image what I was having in my Gmail. So I just downloaded to show you and make you understand. So the thing over here is, in this particular analysis, we have performed two-dimensional analysis. The reason for that was because of the domain what we have created. So domain is nothing but the total control volume where we are performing certain analysis. So in this particular case, the domain was approximately 20 times the diameter of the exit nozzle. So the diameter of the exit nozzle, for example, it is X. Then the length of the domain or the length of this particular region was 20x. So it is a very quite larger domain, and it took me almost 1 to 2 days for completing the simulation. And this particular result what you're watching over here was performed into an 2D analysis, and that too only on the upper half. So you can see a line over here. This is the line of symmetry. The reason for performing the analysis on the upper half was because the particular case is a symmetric case. So whatever is happening on the left hand side will also happen on the right hand side, because the rocket nozzle is a symmetric nozzle. It is axisymmetric. That is the reason we have simplified the case and we have performed the analysis only on the upper half. So you can try to understand over here that 2D modeling is also very important, especially if you are working on these kind of cases. It is not necessary that you have to become a expert in 3-dimensional designing, because 2-dimensional, if you are perfect in 2-dimensional designing, you can create any 3-dimensional body also. Because the rocket what we have created right now is nothing but a combination of 2D sketch that was revolved around the axis. Clear? So for creating this particular geometry, I'll just show you what we have done. I'll just expand. And from this particular location, we have extended the domain to 20 times the diameter of the rocket exit nozzle. The exit nozzle. So this was the domain what we have created. And this was required for us to capture the flow field in this particular region. That is the region after exhausting from the rocket. So these are few examples of axisymmetric bodies and the methodology with which we can work and perform some kind of research. So I hope you have understood very clearly about Revolve option. It is especially used for working with cases that involved diametric presentations of geometries or geometries which are circular in cross section. So that's it for the day, and let us go to the next video.